And now it's exactly expected to be a general phenomenon in number theory. It actually is a fundamental pattern in the prime numbers that somehow has been missed for 100 years. Because why would you want to take it? It's a very strange thing to do.
Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas.
And I'm Marianne Freiberger. The person you heard at the start was Yang-Hui He from the London Institute of Mathematical Sciences, talking about his murmuration conjecture, an exciting new conjecture in number theory that came about thanks to both artificial and human intelligence. And isn't that a really nice name for a mathematical conjecture? I was so intrigued when you told me about this, Rachel.
I know, it's really beautiful, isn't it? So we'll hear about the murmuration conjecture in this podcast. I was talking to Yang about the research program he helped organise at the Isaac Newton Institute in Cambridge, which brought together people working in black holes, people working in quantum gravity, people working in string theory and number theory. And he told us a lot about that program in the last podcast, but he also told us that his role in the conference was to bring along his experience of using artificial intelligence to do research in mathematics. So Yang originally started out studying the interface between the three areas of mathematical physics, string theory, and algebraic geometry. So we asked him how he came to be using machine learning, one of the most significant developments in artificial intelligence, in his work.
In 2017, I got interested in AI. I remember that very well because that's when my son was born. And I had a paternity leave that gave me infinite time at 3 a.m. in the morning, having been woken up to feed them. And then you were like, oh, let's just do something crazy. And so I wrote one of the first papers in just applying machine learning to theoretical science. Because machine learning completely revolutionized, by 2017, every experimental field has been completely taken over. And then NHS, you name it. But then I was thinking, because my background is in geometry, I had, in fact, databases of Calabi-Yau manifolds. So I was like, well, let me just run a simple machine learning algorithm on these databases and just see, can it machine learn it well? And it did. I was very surprised because computing these databases is known to be a double exponential complexity problem.
Calabi-Yau manifolds are fascinating geometric structures. They were discovered by the mathematician Xin-Tun Yao, who won the Fields Medal for this in 1982. You can find out more in our article called Hidden Dimensions. You'll find the link in the show notes. We spoke to Yang about Calabi-Yau manifolds in the last episode, where Yang explained that they provided an answer to a problem in string theory, because they provided the geometry, the structure that was needed to hide the extra dimensions that string theory requires.
So this led to efforts between mathematicians and physicists to try to understand, to classify Calabi-Yau manifolds into different types. And this is something that's actually really difficult to do. So Yang's idea was to use machine learning to help.
In machine learning, you have a task that you might want to perform. For example, you might want to classify things, say a bunch of images, and you want to classify them into whether they are images of cats or images of dogs. But rather than explicitly tell the computer how to do the task, which is what happens in classic traditional computer programs, you have the computer learn how to do the task all by itself, perhaps by spotting patterns in data that you already have. So, for example, you might already have a big set of images to classify, with some of them already labeled correctly as either cat or dog. And then you can design a machine learning algorithm that can learn how to classify images from these ones that have already been labeled. And then it can go ahead and label the rest of the images itself.
So Yang told me that mathematicians and physicists had built many databases of Calabi-Yau manifolds, some with millions of examples. And some of the examples in these existing databases were known to have particular important properties. So rather than check for this explicitly in every example, which is, as he mentioned, very computer intensive, Yang designed a machine learning algorithm to try and spot patterns in the databases that could classify the different examples of manifolds, to spot which ones had important properties, and to learn the landscape of these mathematical objects that were key to string theory.
And so I just wrote this paper called "Deep Learning the Landscape of String Theory," and it's kind of really coincided with several independent groups that also had similar ideas of trying to apply machine learning to understand the string theory landscape. And then I started, oh, this is so cool, right? So I started making friends with everybody. Just like I went, I just giving talks and randomly to seminars and this, and I said, well, give me your favorite problem in your branch of mathematics. It could be group theory, whatever, and let me see what the machine learning actually learns your structure very well. And of course, it works in almost all the cases. So there's something about pattern spotting. So that's how I got into this. But now I'm a little more sophisticated. I'm trying to understand, whether these machine learning algorithms can actually assist us make concrete conjectures.
So Yang's efforts to use machine learning to spot various structures and patterns in different parts of mathematics worked really well in some ways. But Yang said initially in other ways it wasn't much use to mathematicians, as it wasn't really clear what the machine learning algorithms were actually doing. So after struggling for 5 or so years, trying as a mathematician to get something out of this work, Yang's now focusing on using this new, more sophisticated approach to creating new mathematics. He's recently had success with his number theory colleagues Tom Oliver, Qiyon Li, and Alexei Pozdnyakov, where they used a machine learning algorithm to make a concrete mathematical conjecture, the murmuration conjecture.
Yang and his colleagues were interested in something called elliptic curves. These are curves defined by simple equations of a particular form. On the one side of the equation is something squared, and on the other side is a simple cubic equation. So that's where instead of a square you have a power of 3 at the top. These elliptic curves are really important in number theory. For example, when Andrew Wiles famously proved Fermat's last theorem, the proof involved showing that every elliptic curve is equivalent to something called a modular form. Now, we discussed Fermat's last theorem and the idea of modularity with Yang in the last episode.
There's an important property of elliptic curves called their rank, but this turns out to be a really tricky thing to calculate. And in fact, the rank of elliptic curves is involved in one of the unsolved Millennium Prize problems called the Birch-Swinnerton-Dyer conjecture, or BSD conjecture for short, named after Brian Birch and Peter Swinnerton-Dyer. And you can actually win $1 million if you can prove this BSD conjecture. Here's Yang to explain how his conjecture with his colleagues, the murmuration conjecture, came about.
It's called the murmuration conjecture, where we took a database of elliptic curves from number theory, and there is 3.5 million of them, or something huge number, and it has something to do with the BSD conjecture. This is one of the Millennium Prize problems. So this is why the database was set up.
Is that
the Birch-Swinnerton-Dyer conjecture? And then we took this elliptic curves, we were trying to predict its rank, and then of course it predicts as well, right? Because math, there's no accidents. It's very structured data. So we said, well, how do we get interpretability? How do we actually find out what is making it doing so well? So in doing so, we try various algorithms: neural networks, Bayes classifiers, supported vector machines, and they all work. Principal component analysis, the simplest machine learning ever, right? It's just a projection, but that one was the key to it.
Principal component analysis, or PCA, which Yang mentioned here, is a way of taking data and rewriting that data in a different way, in a different lower dimensional space. You can think of this as the machine learning algorithm using PCA was able to give Yang and his colleagues a new, clearer view of the data. In this case, it did this by taking a very unusual type of average of the data.
Lexi, who was an undergraduate intern of Quion at the time, began experimenting with this new way of looking at the data, and he was the very first person to see a very surprising shape.
So when we first saw the plot of this average, it looked like, I remember this, and my collaborators Tom and Kyuhan, they were like, oh yeah, this looks like that stuff that birds do. And I was like, yeah, you mean murmurations of starlings. And then I persisted, and I said, actually, you know what? We should name our paper this, and we got away with it. And now it's called the murmuration conjecture. And then people are still working on it. It's been a year now. The number theory community is still trying to prove a whole sequence of conjectures of the murmuration type. That's kind of interesting. It's kind of interesting now because it required human interpretation, but it would also not have been possible if we didn't do this machine learning experiments. Because so we talked to the really experts like Peter Sarnak at Princeton and all these big names in number theory, because we thought in the beginning it was trivial. We took it to them. And they said, like, is this trivial? And they were like, no, actually. And then they typed, of course, these guys have deep thought about it and say, like, well, Birch could have done this. But he didn't. He didn't take this average. Why? Because why would you take this average? It's such a strange thing to do. And now it's actually expected to be a general phenomenon in number theory. It actually is a fundamental pattern in the prime numbers that somehow has been missed for 100 years. Because why would you want to take it? It's a very strange thing to do. But now it's but really was machine guided, but also human interpreted.
So it's interesting that machine learning could show mathematicians this pattern, and then they could interpret this to understand what insights it could bring to number theory. This work on elliptic curves had connections to the mathematics and physics discussed at the research program at the INI, which we talked about in the last podcast.
Yes, so Yang and his colleagues presented their work on the murmuration conjecture at the Isaac Newton Institute at the conference. And Yang said that a result of the conversations with the many different experts from all the different fields at the conference led them to formulate a new test for the use of AI in furthering mathematics. Here's Yang again.
It's like, given that in the past 5 years have been all these new results in AI-assisted theoretical discovery, let's be more stringent. Let's really test what is a good discovery. And we named it after Birch. So the Birch test is it must pass. So partly this is because ChatGPT has passed the Turing test. So we wanted to have a one up. So it must be entirely generated by AI. 2, it must be interpretable in the sense that if you remove the AI, it'll give a theoretical statement that scientists would work on. So in mathematics, you divorce the AI, anything involved in machine learning statements, and don't mention neural networks. It must be a precise statement for somebody to prove. And 3, it must be non-trivial, in the sense that people will actually work on it. If you just say some random conjecture, they can come up with billions of these. So it must pass these 3. So the murmuration conjecture is one of the few that really, if not the only one, that's almost passed the Birch test, but it hasn't because humans were involved in the interpretation. So according to this strict, and even the DeepMind papers, that was done, this DeepMind paper in 2020, this Nature paper, but it doesn't pass the third one. This is not invariant. They made a conjecture using AI. It was precise enough that it was a conjecture, but they didn't pass the third test because it wasn't non-trivial enough. They were able to actually prove it in a couple of weeks or a month. Whereas the murmuration conjecture passes 2 and 3, but doesn't pass 1 because we were involved in interpreting the results all the time. So far, there hasn't been a single one in mathematics where it's purely generated it's non-trivial and people will work on it. So this is a very stringent. Birch has, of course, very high thing. But that came out from this conference.
Yang told us that it was conversations at the conference between people from physics, from string theory, from number theory and AI, between people from so many different fields that was so stimulating to produce the Birch test and other ideas that came out of the conference. We asked him why having the opportunity, having the time and space to hear from people in fields you don't necessarily work in can be so important in developing new ideas.
I like it because I'm just one, you're never bored, and you always get fresh new ideas that you never think you would do. It fits my personality very well because I'm a pretty manic person. I'm just constantly like, oh, this is fun. It's like dogs with squirrels. It's like, oh, there's a squirrel. It's not everybody has that style. Some people like go deep dive. I just want to work on this problem, and I'm going to spend 50 years of my life on this one thing, which is great. So I think the people describing their hedgehogs and birds, I think that's what they described. Hedgehogs like to burrow deep, and birds like to just take it back and try to see. Right? We need both kinds of theorists. I'm definitely not a hedgehog.
Bird's eye view.
But yeah, I like to see connections between different. Well, I guess that's because of the nature I was raised intellectually. Because my PhD thesis was on 3 different areas that combined together.
That was Yang-Hui He from the London Institute of Mathematical Sciences, explaining that you need all different species of researchers to make mathematics and physics go forward. He was telling us about his work that was part of the research discussed at the program held at the Isaac Newton Institute last year. We've included links in the show notes that will take you to more information about all the things we discussed with Yang in this episode. Or you can visit plus.maths.org/INI. That's it for this podcast. Thanks for listening, and bye for now.